welcome to the House of zk Radio, which is a focused podcast and media channel exploring everything zk, zero knowledge. All right, hi everyone. My name is Alice. I am a host at House of zk. Today I'm joined here with Zac, who is CEO of Aztec. Very excited to be diving into all about zk, privacy, and Aztec with you, Zac.
Awesome. Yeah, thanks for having me on.
Yeah, thanks so much. I'm wondering if we can first start off with an introduction of yourself, and then also what led you to build Aztec based on our current status quo with how we deal with privacy and blockchains, and maybe some limitations and some trade-offs that come in with transparency, with having the pseudonymous kind of model within our blockchain systems. What kind of limitations and gaps currently exist in, say, other solutions that are also trying to address this privacy problem within blockchains?
Yeah, sure thing. Yeah, those are good questions. Should I start with who am I? And move out from there. So yeah, my background is it's not really privacy really or blockchain. It was particle physics originally. I was a researcher who decided the academic life wasn't for me. Became a software engineer, and then from that got involved in startups and Web3 startups. Originally, we were trying to do basically a traditional finance product on Ethereum, and we realized quickly on that we needed strong privacy protections for our users, and that this was a really hard existential problem in a transparent blockchain. And so I started getting involved in understanding zk to solve this problem, doing zk research. My background as a physicist helped there, and basically that led to us developing some quite novel cryptography that solved the privacy problem in a lot of contexts, and then we pivoted using that to basically becoming a privacy infrastructure provider for Web3. When it comes to the kind of the trade-off space in transparent protocols that you were referring to, and the limitations, we're all in Web3. We're all used to this concept of enforced transparency because that's the default status quo. There's a huge amount of selection bias in Web3 because if you care about privacy, it's likely you can't really do anything in this industry. Like, if you want to build an application that needs privacy, you're out of luck, and therefore you're going to tune out of blockchain. And it means that there's an entire universe of applications and products that exists that could really benefit from decentralization, from distributed ledgers that aren't in the room, they're not in the conversation, they're not advocating for their needs because the characters and people involved they just tune out of Web3 because it's all transparent. Without transparency, without privacy, you can't meaningfully talk to real-world systems because you can't bridge that information on chain, and this is creating some very difficult, unpleasant outcomes. I feel like without privacy, there's only two paths for Web3. There's one path where Web3 fails to kind of pierce the Web3 bubble. It fails to talk to real-world systems, and it's basically just tokens that are synthetic, which means that basically like the whole purpose of blockchain really hasn't been fulfilled. And then there's the very dark path, which is that so we do actually start to interact with real-world systems and provide like meaningful financial services, money, etc. to regular people, but it's done without privacy, and at that point you've basically built the infrastructure for a totalitarian surveillance state, because now everybody's financial activity can be surveilled from a single source of data, and it doesn't take much for that technology to be wrapped up in a little bow and sold to governments as a centralized digital ledger. So yeah, I think that privacy is pretty essential.
Yeah, and I really like that point that you mentioned about surveillance as well. And I can see all those challenges in converting a type of system that was designed to be transparent and making it into one that is private. But something that stood out to me with Aztec is that you guys really emphasize providing users with that choice so they can choose whether they want certain aspects to be private or not. So they have that kind of choice. I wanted to dive into a bit more of that idea with providing users with that choice of privacy and talk a bit about the state management mechanism that you guys use. I'm wondering about if you can speak more about the intention behind using the blended state model that you
Yes.
have. So with the from my understanding, UTXO model for private state management and an account-based model for public state management. So
Totally.
can you,
Yeah, let's dive into the details. So, yeah, if you want to handle private state, you need to use a UTXO model because, like Bitcoin, because take the corollary. Imagine if you took Ethereum and you encrypted it all, and then you know all of your transactions were updating this encrypted database using zk proofs. You don't get privacy because Ethereum is an account-based state data structure, which means that if 10 people send you crypto, then each of those transactions is going to be modifying one specific encrypted variable in that database, and that leaks information about who's transacting with who. It leaks the transaction graph. To do actual privacy, you need to use this UTXO structure where basically data, like your state database, contains these discrete values, these notes, effectively, that can be created, but they can't be modified, and they can't even be destroyed, effectively. And so how does that become a useful system? Well, you add on to that UTXOs with this concept of a nullifier. Basically, if I want to encrypt, so let's say I want to create like a shielded Ethereum on Aztec, I will create a note which says, this is one Ethereum, it's owned by Zac. And then if I want to destroy that note, I don't delete it from the database. What I do is I create a nullifier in a different data structure, which basically says that note that was owned by Zac is now considered destroyed. And the key is that the encryption algorithms used to encrypt these two data objects is different. And so they can't be linked. And so if I want to destroy my note, then what I need to do is I need to prove A, that my note exists, and B, that its associated nullifier does not exist. And then I can create the nullifier and destroy it. And so you can use that to create these kinds, like this was pioneered by Zcash and the zero coin protocol originally. Like you can have this kind of join split type of transaction where if I want to send you like value, I'll destroy my node and I'll create a new node which is owned by you. Maybe I'll create a change note with any like residual. So let's say if I have a note worth 2 ETH, I want to send you 1 ETH. I destroy the 2 ETH note. I create a note worth 1 ETH that you own. I create a note worth 1 ETH that I own. This means that basically all state updates are completely unlinkable and untraceable. You can't link a nullifier creation with any existing note that's been generated. So you don't know what's being created, you don't know what's being destroyed. The difficulty here is, now let's say you want to do shared state, where let's just say you're having a decentralized exchange and it has like total supply numbers, liquidity pools. There's logic that needs to be executed over shared global state in order to ensure the protocol is operating correctly. Now that at the moment can't really be done using pure private state because the private state is encrypted, it's effectively owned by somebody, the person who has the decryption keys. And so you can't do that with shared state. Now, there are some workarounds. So there's a company called Tetsei we're partnering with, which is using very advanced multi-party computations to create shared private state. But at a more fundamental level, the model that we have in mind for how Aztec will be used is privacy for the user and transparency for the protocol. If you're interacting with a protocol on chain, then you want to know that it's following its own rules correctly. You want to, if you want to know that you're getting the correct price, a fair price. You want to know that you're being treated fairly, that there's and that no one else is gaining special favors, and that's quite difficult to do in a fully privacy preserving setting. So take an example model of, let's say you're interacting with a decentralized exchange on Aztec. The idea here is that the prices that you're getting and the tokens being transferred within the DEX, that's all transparent, but the identities of the people using that DEX, that's private, that's hidden. And also, if that DEX requires some kind of checks and balances on the users to ensure that they're honest participants, they're not North Koreans, for example, then those checks can be performed privately. For example, you could use a passport signature to prove that you're not on an OFAC sanction list, and that's all happening privately.
Got it. And really like how flexible and composable privacy can be as well. Like what you mentioned, extending privacy to users, but then also transparency to the protocol itself. It's also very exciting to hear how, like, for example, some other tools like multi-party computation can be used to address the shared states as well. So really, really exciting to hear all of that. But just on the topic of these private and public functions, I'm wondering if you can also speak about some of the roles that come with client-side proving and then also the roll-up side proving as well. And also maybe some of the advantages, but then also perhaps some trade-offs between these two approaches when considering factors like scalability, costs, amount of privacy that you can get performance-wise. Just wanted to hear about those two approaches that Aztec uses.
Yeah, it's a very tricky problem. So if within the zk space, right, most zk entities, network startups, they're using zk for computation compression. The idea is you have a very complicated program like that you need to prove, that you need to execute. So you prove the correctness of the execution. You basically say, here are the program outputs, and here's a proof that the outputs are correct. And then that gets verified on chain. The difficulty with that is that these systems are built and designed so that these proofs are generated generally server-side because they're very, very complicated. If you want to prove the correctness of an EVM block, that's a phenomenally complex mathematical operation that you need a lot of centralized compute to execute on. And so that works for a transparent zk blockchain. But if you care about privacy, then that's not a workable model, right? Because if I'm a user, I'm creating a transaction where I'm proving statements about sensitive information. I don't want that information to leave my client device. Therefore, I need to make my transaction proofs locally. And this provides a very interesting and trade-off space. Like up until very recently, the cryptographic technology to execute on this just has not existed. We've been doing a lot of in-house research, pushing the state of the art to make it happen. There's been a lot of research from the entire industry to that pushes in this direction too. But it does also create some interesting trade-offs with regards to the semantics of your smart contracts. Because, see, with Aztec, in an Aztec smart contract, your contract can have public functions and private functions. The private functions modify private state, the public functions modify public state. And private functions can call public functions. But public functions can't call private functions. And why is that? It's because the actual execution of these functions is time asynchronous. Because as a user, if let's say I'm generating a transaction where lots of smart contracts are being called, lots of functions are being called, I am going to locally on my device, I'm going to prove the correctness of the private functions. So what I'm going to get out is I'm going to get out a zero-knowledge proof, and there's going to be public inputs of that proof that will describe the encrypted notes I want to add to the encrypted state tree, encrypted nullifiers I want to create, any encrypted events I want to emit, and public functions to call. And then that transaction gets thrown into a mempool, it gets picked up by a sequencer, and at that point, then when the roll-up proof, zk roll proof is being made, then those public functions get executed. And this is necessary because when you have public state that's account-based, then you have race conditions, basically, because I, as a user, I don't know the latest state of the blockchain. So I cannot prove I can't make proofs of my public function calls because I don't the state values I'm modifying. I don't know their accurate values. Whereas in the private land, I do because with this UTXO nullifier model, UTXOs can only be created and nullifiers can only be created. So if I prove that a UTXO existed at some point in the past, it exists in the present. That's not the case with public state. And so you need a sequencer to order your transactions in a block and then execute the public functions. And so that creates an interesting problem where, okay, well, if the public functions are executed after the private functions, how do I create smart contract semantics that handle that without it becoming a complicated mess? And what we settled on is effectively the public functions that you call from your smart contracts, from your private functions, they can't have return parameters. So if you're calling a public function, you can provide input parameters, but there's no return parameters. And so effectively what that means is that what happens in the public space cannot really overlap with what happens in the private space. As in, because the public function is modified public state, private function is modified private state. You don't the execution of the two have become decoupled, so you can execute them out of order. Now you may ask, well, what's the use of calling a public function that doesn't have return parameters? Well, some basic things are you can do assertions in a public function. So I could, if you're doing some kind of time-gated activity, you could in a public function validate that, the block time is beyond a certain point, or you can also execute these hybrid transactions. So there's quite a few transaction profiles where you need to modify public and private state. An example of this is if you want to interact with a decentralized exchange. You start out with shielded nodes. And what you do, like we've created some abstractions that make this pretty seamless to program, but under the hood what's happening is you are, as a user, you're unshielding your nodes into a random address. And then that random address, that random account is calling the decentralized exchange and performing a swap on public quantities. And then once those swaps have occurred, that random address is going to shield the output, the output of that DeFi transaction is going to shield it back into private nodes that are owned by the original user. And so in that kind of model, people see the values of the trades being executed, but they don't know who's executing the trade. And that requires a sequence of private and then public function calls. And that can all happen in a single atomic transaction using the semantics we've created.
Wow, so you can complete that hybrid transaction as well within
Yes.
that same model. Wow, yeah, that's very impressive.
Thank you.
Yeah, I see like a lot of different use cases for when you're trying to address both the public and then also private states like simultaneously. So that sounds all great. And I wanted to also dive into more of the motivations behind certain architectural design considerations that the Aztec team made. So in terms of the proving system, Aztec uses Honk, and I'm wondering if you can speak more about some of the enhancements that were made on top of Plonk for Honk, and then also, from my understanding, you also use Goblin Plonk for recursion, and then also Proto-Galaxy as a lookup scheme. So wondering if you can also speak about how they compare to other recursion techniques and other types of existing lookup schemes as well.
So Aztec uses a very unique cryptographic technology stack. I think pretty much every single other zkL2 out there uses protocols based around hash functions, error correcting codes, not elliptic curves. Elliptic curves are kind of a bit of an old school technology these days. But we've gone in a very different direction because of the very different requirements of the Aztec network. So fundamentally, what do we need in Aztec? We need to be able to generate zero-knowledge proofs in hardware-constrained environments with a minimal amount of memory consumption. Because if you're in a phone, you probably have a gigabyte of RAM. If you're working in a web browser, you have 4 gigabytes of RAM. And we also need very, very fast recursive proof composition. Because take that example I talked about earlier, like where you have contracts, you have a transaction where you're calling a contract, that contract calls another contract, that calls another contract, calls another contract. Like these contracts are all written by different entities. And so each contract, basically every function in the smart contract is its own zk-SNARK circuit, its own zk-SNARK verification key. And these all need to be composed together recursively to create a single atomic transaction. Like basically the actual zero-knowledge proof that the user is generating is verifying recursively all of the zero-knowledge proofs generated for each single function call, and then like composing them together, handling state transitions, very, very complicated stuff. And so you need very, very fast recursion client side. And this is an extremely difficult problem. When I started working in the space, recursion wasn't really possible, practical. When we built Aztec Connect, it was like we created the first viable recursion techniques that could be used inside a smart contract ecosystem, but that was server-side recursion. So like Aztec Connect, Aztec 2, that was in 2020, and to recurse you could do it, but you needed a big chunky server. It took a lot of time. Nowadays we need to recurse at a level of about 20 to 100 milliseconds in a web browser, and so. Yeah, so when it comes to the proving system, how do we handle all of this? Well, first of all, Honk the core proving system is Honk, which is basically the original Plonk protocol from 2019, but with some modifications. The interactive oracle proof that Plonk used was quotient testing, effectively. You have some polynomial algebra that is equal to 0 modulo a vanishing polynomial. And that's quite memory intensive because it requires fast Fourier transforms which blow up the memory that you need. Some checks are very nice in that the amount of memory that's consumed is basically 1.5 times the size of your execution trace. It's basically as small as it gets. So we use a sum check interactive oracle proof. We also add in a lot of extra, we call them custom gates, basically. Instead of just having a basic addition gate, we have gates to do Poseidon hash functions, elliptic curve primitives, efficient range checking. We have a sub-protocol within Honk which handles efficient memory checking techniques. So you can get like a RAM abstraction, where you basically have an array and you're reading and writing into that array at arbitrary points. As well as a lookup protocol, logup at the moment, which is a derivative, which was a big improvement on lookup, which we published in 2020. And so, that's the core proving system, and it's relative to the original Plonk, is extraordinarily performant. When I said, did I say? I can't remember if I said it on this podcast or in the talk I just gave. But so if you want to do a zk email proof with Noir, you can do that. I think the latest is 5 seconds on a phone, I believe. And that's like a very complicated proof requiring a lot of SHA hashing, RSA signatures, very nasty stuff. But then that doesn't solve recursion, right? Because now if I have this Honk proof, well, in theory recursion can be fast because the thing about elliptic curve proofs is that they're succinct, they're small, and the verifiers are very short, which is very important. But the challenge is twofold. Pun slightly intended. So we use folding schemes, as you mentioned, to handle recursion. Technically, folding is not recursion, but I'm kind of using the two interchangeably because you get the same outcomes. What a folding scheme is instead of having a zk-SNARK circuit where you're running the verification algorithm to verify another zk-SNARK proof, what you're doing is you're mashing together you basically have these you take basically the start of a proof. So you basically have the commitments to your execution trace of your program. So you have a satisfying assignment of your circuit, and you create random linear combinations of these. You basically mash them together instead of actually verifying them. It's a very powerful primitive. The way it's hard to explain without a whiteboard. But with something like Honk, right? What the proving system is doing, what the crypto system is doing, is you have some complicated polynomial expression which is supposed to equal 0. And then you run a prove and verify algorithm to check that it equals 0. With folding schemes, what happens is when you mash these instances together, the result is no longer 0, right? Because you've just created random linear combinations of two different circuits, and then you're running then eventually you're going to run the Honk verifier, and the output is not going to be 0. But it's going to be equal to some kind of error term. And with what the folding scheme does is basically you have a protocol between a prover and a verifier where the prover basically says, here, I'm going to mash these instances together, and instead of the results, instead of the Honk protocol producing 0, it's going to produce an error term, and then you run a folding prover and a folding verifier algorithm to validate that error term is correct. And this is much, much faster than actually brute force verifying your proofs. So it was a huge advancement for us when this stuff came out, and so we implemented it pretty as soon as we could. So folding schemes partially solve the recursion problem, but they don't. For elliptic curves, they don't solve the big problem. One second. The big problem is this concept of a non-native curve arithmetic. So if I want to run a folding verifier in my SNARK circuit, then that requires elliptic curve arithmetic. And it's a kind of an infamous problem with elliptic curve crypto that if you're trying to verify a proof on if you're trying to verify an elliptic curve proof within an elliptic curve SNARK and you're using the same elliptic curve, then the arithmetic you need to evaluate is over a prime field that's different to the native prime field that your circuit algebra is being checked over, and that makes it very inefficient. And so that's where Goblin Plonk comes in. It's a very it's a very detailed, complicated, messy real protocol. But what it does is effectively it takes all of these non-native elliptic curve operations that need to be performed, and it transforms them into native elliptic curve operations. Which provides a massive reduction in complexity. It means that the cost of verification drops from like 300,000 constraints, Planckish constraints, to like 16,000. So yeah, it's basically like the way I like describe Goblin Planck is like it's a folding accelerator. It basically takes the expensive parts of folding and it makes them very cheap. And so you combine folding and Goblin Planck, and we have outrageously fast recursion, like lightning fast recursion, the kind of that you can't really get from any other proving system, because we're leveraging the succinctness of the elliptic curve crypto with the benefits of folding schemes, which for the most efficient ones require additively homomorphic commitment schemes, which again you get from elliptic curves, and then we're using Goblin Planck to basically completely bypass the traditional downsides that you get with this approach. And so, yeah, that was the kind of the last missing ingredient we needed to make the Aztec network's cryptography possible.
Got it. It's very fascinating to see all the techniques that went behind, like the kind of the back end of this system, and trying to make that final proof more succinct, less costly, and while accounting for things like memory constraints. So it's always very fascinating to see all those design considerations. And
sorry, can I touch on? Sorry to interrupt. Can I touch on one thing, which is I just remembered I'd like to bring up, which is there's something a problem that we ran into, which is very, very subtle and very significant, that is not really widely disseminated when it comes to building privacy-preserving networks. So generally, every hash-based crypto is dominating right now because it's, in terms of raw performance, if you don't care about recursion too much and you don't care about memory consumption too much, in terms of raw performance, it's fantastic. But the proof sizes are quite large. And normally this isn't considered a problem, right? Because you just use recursion, and eventually, if you're producing like a zkL2 block, you're only sending one proof on chain, and then you just wrap that in Groth 16 or something to make it a succinct job done. But now consider the scenario of Aztec, right? Where, because it's privacy preserving, every single user transaction is a zero-knowledge proof. Now imagine you want to build a decentralized L2 where you have 1,000 TPS, transactions throughput. And imagine now every single user is creating a transaction where the proof is 100 kilobytes large because it's using hash-based systems. That means that the raw network bandwidth that you need is 100 megabytes per second for 1,000 TPS. And that's the network throughput. But the actual bandwidth that your nodes need, because it's a peer-to-peer node, is substantially higher than that. We're talking multiple gigabytes a second, which is not possible with broadband connections today. And this is an existential problem when it comes to building privacy networks, which is preventing us from using hash-based crypto, because the traditional solution to this is, okay, well, if the proof is too large, you just compress it, right? Like, let's you verify your hash-based proving system in something like Groth 16 or Planck, and then you get a small proof. The problem with that is that it's very time-consuming and very computationally intensive. The time-consuming part is problematic because it affects the transaction latency, because my transaction cannot hit the mempool until that compression has occurred, which means that the time taken to compress is going to be added onto the time required for my transaction to be confirmed, and therefore the amount of time I have to wait before I can send another transaction. So if I want to send multiple transactions that build on top of each other, that becomes deeply, deeply problematic. And also, it's relatively computationally intensive. I think that right now, I was looking at some benchmarks published online. I think it's like a minute right now. Maybe it can get reduced for 10 seconds with GPUs. But regardless, it's quite a lot of work. And it presents a doxing risk for a decentralized network, because this work has to be done by a third party before the transaction hits the mempool. And therefore, the entity doing that work does not know if they're going to get paid. As in, they can't just extract a fee from the transaction because they don't know the transaction is going to get mined. And as a malicious user, I could very easily dox that kind of network by sending a ton of transactions to get compressed, and then and then but ensure that they never get mined by then once those compressed transactions hit the mempool, I send another compressed transaction which invalidates them all. So this is kind of an existential problem. Which is another reason why we're staying with elliptic curve-based crypto, because if you're using elliptic curves, then the proof that the user is spitting out can be very small. I think so. Right now, because the Aztec network, we just want to get it launched. We're not targeting 1,000 TPS on launch. We're targeting much more modest numbers. We don't care about proof size yet, but in a year we will. And with a small amount of engineering effort, we can get our proof sizes down to 8 kilobytes. As opposed to I think the latest state of the art with hash-based is like 40 or 50 kilobytes.
Oh, wow. So yeah, very impressive to see, all of these improvements being made. Very recently, I mean, there's a huge improvement in terms of lowering the proof size and then also proving costs that we've been seeing in the past few years. And it's great to hear that the Aztec team is, taking those into consideration, at least for the long term. That all sounds great. And just as a last question before we close, I'm wondering if you can speak about some use cases that are currently being built on the Aztec ecosystem or using Noir, which is your guys' zkDSL, some that you're excited about, or some use cases that maybe haven't been built yet, but you would like to see in the future.
Totally happy to. That's something I'm really excited about in 2025, because normally when I'm on a podcast talking about Aztec, talking about applications, I'm talking about hypotheticals. I'm talking about what people could build because our tech wasn't advanced enough. But now it is. Some of the things I'm very excited about are, so we have ZK Passport, which is a team building with Aztec technology. They are basically, when passports today, they have chips in them that will sign digital signatures when they're next to an NFC scanner, and your phone is an NFC scanner. So what you can do is they have a little app where you tap your passport with your phone, it extracts a passport signature, and then it wraps that in ZK to selectively disclose information. So normally that passport signature can be used to extract the whole shebang about who you are, your name, your address, your passport picture, blah, blah, blah. But with this technique, you can selectively disclose. So you can say I am a US citizen, or I'm a British citizen, or I'm over 18, but you can choose what to reveal. And that's all done with Noir. I find that very exciting because it gives you literal passport-grade identity authentication within a smart contract ecosystem. Another thing I'm very excited about, which is kind of more recent, is so we ran a little hacker house in January in London, and one of the teams there used the open banking API to create peer-to-peer on and offboarding into crypto. So the open banking API is banks in the EU and the UK are forced by law to expose an API which you can talk to initiate financial transactions. There's some regulatory compliance stuff, but fundamentally the idea is you can ping a server and just to initiate a transaction from an account, and the bank will send back a response indicating that they performed that transaction, and that response is digitally signed by the bank, and so you can use that to perform peer-to-peer on and offboarding into crypto. So to give an example, let's say I want US dollars and you want USDC. I can put USDC into a smart contract, and basically that smart contract will say, I will give you this USDC if you can provide a open banking a proof that you basically sent Zac $10 from the open banking API. And so that then gets effectively bundled up into what looks like an atomic transaction, and enables completely trustless on and offboarding from crypto, peer-to-peer. You and I, we don't have to know each other, we don't have to trust each other, but we can still interact in that way. And they got a demo working using that API. They got a demo working in the hacker house, and it was mind-blowing. We have people building private security tokens with Noir. There's Anoncast, which built in a weekend with Noir, which allows you to anonymously post from social media. The idea is, if you prove in zk that you possess some Anoncast tokens, then you can tweet from the Anoncast Farcaster account or Twitter account. So I'm really excited by all these use cases and applications. I'm excited by the work that like Tatseo is doing to do shared private state in Aztec, and what that enables. I'm excited by, there's teams building wallets on the Aztec network that enable, private cryptocurrency transfers and private DeFi, which I find incredibly exciting. And so, yeah, it's a real renaissance, I think. Take that hacker house in January, for example. I've been around in crypto and Web3 for eight years now. And when I was getting into crypto, I was going to hackathons, I was going to hacker houses, and the vibe of these places was very energizing because people were building very ambitious products and systems. They're trying to do things like supply chain, real-world assets, like land registry deeds. They were trying to do insurance. They're trying to do law, legal documents, and like all these very ambitious, high-minded things. Which, in hindsight, back then, the technology wasn't capable. You go to a hackathon today on Solana or something, or a transparent layer 2, and you don't get that anymore, right? Because people have become too jaded. Because they know that you can't build those kinds of systems in a transparent way. But that's what people were building at Aztec's Hacker House. Like real world payments using that open banking API. Like supply chain projects, and they're getting demos working end to end in that hacker house. The technology is here now, and so I was very excited by that. Like that that finally we can start to meaningfully execute on the ambitious visions that people had 10 years ago, when this technology when Ethereum was brand new.
Yeah, absolutely. The time is here, and it's very exciting to hear how extensive the amount of applications can be in both like Web3 and non-Web3 scenarios as well, like what you mentioned with identity verification, even with supply chain as well. So it's very exciting to hear all those applications. And thank you so much, Zac, for coming on to our podcast today. Really enjoyed overall hearing both the kind of technical nuances with your design considerations, but then also the vision behind why Aztec wants to form the new privacy landscape, and then also some of the applications as well. So really enjoyed the conversation today.
Thank you very much. Thank you. Likewise, this has been really a real pleasure. Thank you for having me on.
Yeah, of course. Thank you so much.